Good morning, students. Today we will discuss the physical properties of aldehydes and ketones. Lower aldehydes, they are generally liquid in state, whereas the higher aldehydes and ketones, they will be in the solid state. For example, if we take methanol, student, it's an exceptional case which is a gaseous in state, right? Whereas rest of the aldehydes, lower aldehydes, they are liquid, and the higher aldehydes will be the solid in state. Similarly, the ketones, they, whether it be a lower ketone or the high ketones, they are generally solid in state, right? Or in the liquid state. Lower ketones will be in the liquid state, whereas the higher ketones will be in the solid state. Now the state is clear that the general state, we can say it is liquid, and the higher one is going to be the solid state. Exception is HCHO, which is in gaseous state, right? Now come to the solubility. Students, you know that the ketone or the aldehyde, they have got carbonyl group attached to it, right? The carbonyl group, it is polar in nature and it forms hydrogen bond. It undergoes the intermolecular hydrogen bonding with the water, right? Though the intensity will be less, but it undergoes the hydrogen bonding. As a result, the lower aldehydes and ketones are soluble in water. But students, when we talk about the higher aldehydes and ketones, as the size of the alkyl group or the hydrocarbon chain, it will increase, the solubility is going to decrease due to the hydrophobic nature of alkyl group, right? So the higher aldehydes and ketones are less soluble due to presence of hydrophobic alkyl group increase in size, right? So as the size is going to increase, the hydrophobic nature is going to increase. But if we compare the solubility of aldehydes and ketones with the alcohol are more soluble in water than the aldehydes and ketones. Now coming to the boiling point, student. So due to the dipolar interaction caused by C-double bond O, you know that we have discussed the resonating structure of it, and we have found that the carbon will get positive charge and oxygen will get negative charge. So there will be a dipolar interaction between the nearby aldehyde or ketone. So due to dipolar interaction, boiling point is higher than corresponding alkane, that is their parent alkane from which they have been derived, or the ether, right? But student, if we compare the boiling point of alcohol and the carbonyl compound, that is aldehyde and ketone, the boiling point of alcohol will be more, as it forms the intermolecular hydrogen bonding, whose magnitude is very less, or we can say that carbonyl compounds that don't get associated with one another through the intermolecular hydrogen bond, right? So if we compare aldehydes, ketones with the alcohol in terms of their boiling point, so which will have the higher boiling point, it is alcohol, right? And the boiling point of alcohol is more than aldehyde and ketone, right? As they contain the intermolecular hydrogen bond. As they form intermolecular hydrogen bond. Right, student? So these are the main physical properties of the aldehydes and ketones. Next, students, we will discuss the chemical properties of aldehyde and ketones. Now, to begin with the chemical properties, we have to keep in mind that the carbonyl group, it is polar in nature, right? So let us take an example. If it is in this way, which is in this way, so we have got the carbonyl group in this way, right? So here we know that the carbon is sp2 hybridized. So here it is having planar shape, and it is sp2 hybridized carbon atom, right? So when a nucleophile will attack it, so you know that it is getting in this way, right? Due to the resonance, can show that the oxygen will get a negative charge due to pi bond shifting, and carbon will get a positive charge, right? So when the nucleophile will attack, the step is slow step. Now what will happen here? It will get the shape changed in this way, right? Now this is the tetrahedral structure of the addition product which has been formed, right? And here sp hybridization, the hybridization of carbon has changed to sp3, right? So I have encircled here carbon. This is carbon here. It is undergoing sp3 hybridization, right? Now under the presence of we can say in the presence of proton hydrogen, right? This takes hydrogen ion. We will get it in this way. Here the nucleophile will be there. This is there, and here we will get OH. So this is the reaction which is taking place, and in this way the nucleophilic addition will take place. So due to the presence of the polar carbonyl group, right, the aldehydes and ketones, whether it is aldehyde or it is a ketone, it will undergo nucleophilic addition reaction. It can be either an acid catalyzed or it can be a base catalyzed also, right? Now we will discuss certain examples of the chemical properties which is showing the nucleophilic addition reaction. Students, the nucleophilic addition reactions of these compounds we will study in two heads. One is where there is no elimination of water, and other where there is only addition, and other is the where there is a nucleophilic addition along with the elimination of water molecule. Okay. Now students, before we will discuss the examples of nucleophilic addition reaction, now just check the reactivity of the aldehydes and ketones for the nucleophilic addition reaction. What I mean to say here is that comparison of aliphatic aldehydes and aliphatic ketones toward nucleophilic addition reaction. Nucleophilic addition reaction. Right? So if you compare, let us take this example RCH. This is an aldehyde, aliphatic aldehyde, and this is aliphatic ketone here. So among these two, which one will be more susceptible to the nucleophilic addition reaction? Right? So here the more susceptible will be this aliphatic aldehyde, and this can be explained through the plus sign effect and through the steric hindrance. Right? And among the two, if we compare, the formaldehyde will be more reactive toward the nucleophilic addition reaction, right? So the inductive effect, due to inductive effect, the polar nature, we can say that the positive charge due to which the nucleophile is attacking on this carbon, this electrophilic center, right? The magnitude of the positive charge get decreased, right, due to the plus I effect. Right? So here we have got two alkyl groups. That means the magnitude of the positive charge on the carbon atom will be reduced to greater extent. Right? And where aldehyde for methanol has got no alkyl group, here the intensity of the positive charge on the carbon atom, it will be retained. Right? It will be maintained. So hence from the inductive effect concept, the formaldehyde is more reactive toward the nucleophilic addition reaction. Right? And if we check the steric hindrance, students, here we don't have any bulky group, right, which will cause the hindrance to the path of the nucleophile. Whereas here we have got one alkyl group and here we have two alkyl group. So if we compare the aldehydes and ketones, students, due to presence of the two alkyl group, the carbonyl carbon is sterically hindered and hence the nucleophile will not get easily attacked to it. Right? This was when we comparing aliphatic aldehyde and aliphatic ketones. Now just check the the aliphatic reactivity of aliphatic aldehyde and aromatic aldehyde or aliphatic ketones with aromatic ketones. Now let's take example here. If I have this RCHO, we are comparing its reactivity, let it be CH3 here, with the benzaldehyde C6H5CHO. This is benzaldehyde. Among the two, students, which one is going to be more reactive toward the nucleophilic addition is the aliphatic aldehyde. Why? Because the aromatic aldehydes here, due to resonance, right, the positive charge on the carbon, it will be reduced and hence the nucleophilic attack will not be easily taking place. Right. So if you draw the resonating structure of benzaldehyde, right, this is there plus coming here, so it will be pulled in this way. So you can see that the positive charge on the carbon atom is not here. Right, you can see that. So as a result, what will happen? The nucleophilic attack will not be smoothly taking place. Right. So when you draw the resonating structures further in this way, so it will be coming here. We will get positive charge here. For the resonating structure, one more if you will draw. Spaces, I am drawing it here. So you will get here bond but a positive charge here. So you can see that in these resonating structure we are not getting the positive charge on the carbon atom. So how the nucleophilic attack will be taking place? Right? It will be only taking place because of the first resonating structure. So we can say that due to resonance, the magnitude of the positive charge on the carbonyl carbon, it gets reduced. Right? It is due to plus R effect, the electrons are released toward the carbon atom of the carbonyl group, right? And the electron density at the carbon of the carbonyl group increases. This decreases the magnitude of the positive charge on it. Right? Now, here it is clear now to you that among the aromatic aldehydes or ketones, in a similar way you can draw for the benzophenone also. Right? Now, let's compare the reactivity. I am drawing here CH3, CHO, right? Then we have here benzaldehyde C6H5, CHO. Then we have C6H5, COCH3, and then we have C6H5, COC6H5. Now, if you check the reactivity here, this is going to be more reactive. Right, benzaldehyde less. Here we have got an alkyl group. Again, it is going to be less, and this is going to be the least. right? Again due to plus I effect and due to the steric hindrance, right? So now we will discuss the chemical properties, chemical reactions where the nucleophilic addition reactions are taking place without elimination of water molecule.